In this video I'm going to talk about the boundedness theorem. So it states that if a function f of x is continuous on the closed interval from a to b, it's important that it's a closed interval, then it is bounded on the same interval. So let's consider the proof. So suppose that it is not true. So we are going to prove it by contradiction. So suppose that it is unbounded. Suppose that it is unbounded. Is unbounded. So what this means, basically by definition of a bounded function, what it means is that that for any natural number n, there exists some x in this interval from a to b, such that the function f of x is greater than n. So this is unbounded. This is unbounded from above. Like we can similarly consider the bounded from below. So these are two symmetrical cases. We can just prove one of them, and the other would be kind of by symmetry would follow automatically. So the proof would be similar. So basically suppose that it is unbounded. Like here we need to suppose that it is unbounded from above. So if we prove a contradiction in this case, then similarly we can prove a contradiction when it is unbounded from below. Therefore, the ultimate conclusion that it is unbounded, that it is bounded from both below and from above. Okay, so for any n we can find such x. So let's construct a sequence. So for any, since this holds for any natural number n, so we consider a sequence of we consider n to be equal 1, 2, 3, and so on. So for any natural number, so this would from this we construct a sequence of x1, x2, x3, and so on, such x that exist by this condition. So we construct this sequence this way. So because this holds, so for every n, like xn belongs to AB, and also f of xn is greater than n. So this is by construction. So okay, so now we notice that this sequence xn it's itself bounded. So the sequence xn is bounded. This is because all xn belong to the interval from a to b. So all of them, we can write it this way: xn less or equal than a, and xn greater or equal than a, and less than or equal than b. So it is bounded. So therefore, by the Balzano-Weierstrass theorem, there exists a convergent subsequence. So since it is bounded, so by Balzano-Weierstrass theorem, by Balzano-Weierstrass theorem exists a convergent subsequence. Subsequence of xn. So we take this, so let's say the convergent subsequence is xnk, when k varies from 1 to infinity. So this is the convergent subsequence, so it converges to some limit. Let's say it converges to limit c when k tends to infinity. Okay, so so now we remember that we had a condition on f of xn, so f of xn. Oh yeah, before we recall this condition, so first we use continuity. So because we have a sequence that is convergent, we can use the continuity of function f. So so from this we conclude by the continuity of the function f, we conclude that f of x and k, it converges to f of c. And yeah, by the way, c belongs to ab also. C belongs to, so here I write c belongs to ab because the interval ab is closed. So like if all x and k belongs to ab, then the limit also belongs to ak because of the closedness of the interval. Okay. So now because the sequence converges to a number in the interval, and the f of x is continuous on the interval ab. So because of that, we conclude that f of x and k tends to c, tends to f of c when k tends to infinity. So, but this means that in particular that f of x and k is bounded. This sequence is bounded because a convergent sequence is always bounded. There is a theorem that says that if a sequence of real numbers converges, then it is bounded. So, but this contradicts the condition that I showed above. This contradicts this because this basically this states exactly that f of xn is unbounded. So like if we rewrite this condition for nk instead of n, so nk is a subsequence of and so we write that f of x and k is greater than nk. Okay, and nk is a subsequence of n, right? So nk is a subsequence. Subsequence of natural numbers. Fine. Therefore, we can write that this is greater or equal than k, because all nk must be different. So basically, this means that this sequence is unbounded by definition of boundedness. Therefore, f of x and k is as a sequence by k is unbounded. And we just proved that it is bounded. So this condition and this condition contradict each other. So this is contradiction. Yeah, so this contradiction concludes the proof.